All right, let's go ahead and get started. So this is Linkerd 101. Thank you all for tuning in. I think this is going to be a lot of fun. So I encourage you all to ask questions. You kind of have two options for asking questions. Any questions that are submitted using the link that's at the top of the presentation, I'm going to answer those at the end or try to get to as many as I can. So if you want me to answer a question, you can use that link. Otherwise, you can sign into our Slack, slack.linkerd.io, and go to the Linkerd 101 channel, and there'll be some more Buoyant employees who will be answering questions there. So if you want to ask a question in the Slack, they'll answer it there. If you use the link at the top of the presentation, I'll answer as many of those as I can at the end. So a little bit about me. My name is Alex. I'm a software engineer at Buoyant. I work on Linkerd. Originally, I am from Canada, and you can follow me on Twitter if you like. And before we really get started in earnest, just a quick word about our sponsor. So Buoyant is the company that I work for. We sponsor the majority of Linkerd development, and we also provide things like training and commercial support for Linkerd, as well as building enterprise features on top of Linkerd. So if any of that sounds interesting to you at all, please get in touch with William. His email address is right there, or you can find him on the Linkerd Slack as well. So please get in touch with him if any of that stuff is of interest to you. Okay, so we're going to be talking about Linkerd today. We're going to talk about what Linkerd is, where it fits in your stack, what it does, why is it useful, and why might you want to use it. We're going to talk about different deployment models, how it kind of fits in with your application, and how you deploy it. Then we'll go into a little bit more detail on how it works. In particular, when Linkerd receives a request, what happens to that request, and what are the steps involved. After that, we'll talk about Dtabs and dynamic routing, which are some of the more powerful features of Linkerd that really kind of showcase the cool stuff that it can do. And then at the end, we'll have some time for questions. So that will be time for me to answer any of the questions that have been submitted using the link at the top of the presentation. So to begin, what is Linkerd and why should you care about it? So Linkerd is a layer 5 proxy. And what that means, layer 5, refers to the fact that it deals with protocols like HTTP, Thrift, MUX, HTTP2, gRPC, and so on. And these are all protocols that have requests and responses. So we're not talking about raw TCP packets, we're talking about request response. And that's really important because it means that Linkerd can orient itself around these request level concepts like what is a success, what is a failure, what is the latency, how long does it take to process a request and response. And these are things that you can't really talk about if you're just talking about raw TCP packets. You really need to be talking about request response. And proxy means that Linkerd receives requests, you send requests to it, and it forwards those requests on to the final destination. Linkerd is based on an open source library called Finagle that was developed at Twitter. Finagle is extremely battle tested. It takes millions or billions of requests per day at Twitter and many other companies that use it. And we chose to kind of use this as our starting point because it's so well tested. It's been through countless incidents, and it's been very well exercised and very well production tested. And that's what we use as the starting point and the base for Linkerd. The thing that is a little bit limiting about Finagle is that it's a library and it's written in Scala, which means that you can only really use it if your application is written on the JVM. So Linkerd, in contrast, is a proxy. It runs as a standalone process. It's not a library. And so any application that can send requests, like HTTP requests, for example, to Linkerd is able to take advantage of all of that. So there's no need to write your application in any particular language. It works in any language, and it works in any environment. Okay, so why do you even need something like this in the first place? What's the point? So one of the first things that Linkerd gives you right out of the box is service discovery. So if your applications are running in a scheduled environment like Kubernetes or like Mesos or Docker Swarm, applications will move around as they get rescheduled. And you need to be able to keep track of them in order to send them requests. So Linkerd integrates with all kinds of service discovery schemes like Kubernetes, Marathon, Aurora, Console, and we keep track of the locations of all the instances so that when you send requests to Linkerd, it can forward those to the correct location, and you don't need any of that code in your application. So service discovery is something you absolutely need if you're in one of these environments. Linkerd can do intelligent load balancing. So rather than just doing round robin or something like that, we can take a look at historical latency data for requests. And we can say, oh, these particular endpoints are slow, so we're going to send them less traffic. These ones are fast, so we're going to send them more traffic. And we can make really intelligent load balancing decisions based on that information that we have. And if you want to hear more about this, we have a really great blog post. I'll put a link at the end of the presentation on how good load balancing can really improve your tail latencies. We also do retries. So this is kind of one of the best ways to easily improve your success rate is you can add automatic retries to your application using Linkerd. If a request fails, Linkerd can know whether it's safe to retry and send another request and hopefully be successful the second time. The next thing that Linkerd can add that's really powerful are circuit breakers. And what this means is that if one endpoint that you're talking to is unhealthy, something has gone wrong with it, it's in a bad state, and it's failing requests, we can be intelligent about that, and we can stop sending traffic to that one endpoint. We can cut it off, and it will no longer affect your success rate. It will no longer take your service down. You can just kind of cut off traffic there. And we will over time, attempt to send more traffic there, little by little, and once it becomes healthy again, we'll turn it back on. But as long as it's unhealthy, we'll stop sending traffic there and won't let one bad instance, take down your whole service. And using Linkerd means that you get request level metrics and tracing throughout your whole stack kind of for free. So Linkerd will record very rich data on success rate, latencies, connections, all kinds of things that are really useful and expose that. So it kind of gives you all this instrumentation without needing to build it into your application. And we also do distributed tracing. So we'll emit traces that can be used for Zipkin or open tracing, and you can get a topology of your application. You can see these traces. And lots of other things. Transport security, timeout, deadlines, lots of cool stuff, some of which we'll talk about later in the presentation. And the great thing about having a process like Linkerd do this is that these problems, any individual one of them, you could theoretically build the code into your application to do this, but these things can be tricky and it's easy to get them wrong. And it's just really nice to be able to rely on this code from Finagle that's so well tested and has all the corner cases exercised, and you kind of know that it's going to behave well at scale. And applications shouldn't have to kind of reinvent this wheel all the time. This is kind of, some of these problems have already been solved. We should be able to take advantage of that. And libraries, are appealing because you can centralize the code, but the fact that they're language specific is really limiting. And so Linkerd, by running as a standalone proxy, lets us circumnavigate that. And it means that even if your application is written in many different languages, you've got this uniform network layer across your whole stack. So you get uniform metrics, for example, across your processes that are written in Python or Go or Ruby or what have you. And it's really, really nice. So Linkerd always comes with a config file that configures how it's going to work. We're not going to go line by line into this, but I just wanted to take a look at kind of the high-level structure of the config so that we kind of know what the high-level concepts in Linkerd are. So in this example config, there's three kind of sections that you should be aware of. The first section up there is the namers, and namers are things that will integrate with service discovery. So you might have a namer to talk to the Kubernetes API to find out where your Kubernetes pods are running. You might have a namer that talks to console to find out where your console services are. And so this block kind of defines that integration point. The next thing is we've got two routers defined. And a router is kind of the basic building block of Linkerd. A router is a piece of software that's going to accept requests and it's going to forward them on to their destination. And so we have two routers here that work slightly differently. So if we drill down into what a router looks like, there's kind of two sections that we want to take a look at. One is a section of routing rules, and that's called a Dtab. We're going to talk about that in more detail later in the presentation. But for now, we can just say that's a list of rules that determine how this router is going to route requests. And then the second part there is a list of servers, and those are the entry points into the router. Those specify where Linkerd is going to listen for incoming requests. So once Linkerd is running, you start it with a config file and it boots up. This is kind of the basic structure of what a router looks like. So on the left, you've got a list of servers. Those are the entry points into the router. Those will listen on a specific port, and your application will send requests to those servers. Then the router will do some fancy, complicated routing, and it will then send those requests using a client to some specific destination. Now what's interesting to note here is that on the left side, those servers are statically configured. You specify those in your config file. But on the right-hand side, those clients are all dynamically generated. So based on the properties of the request and based on what routing rules you have, Linkerd will figure out what kind of client to allocate in order to serve that request. Linkerd has a very cool dashboard that kind of gives you some insight into what it's doing and what's going on. So by default, this is served on port 9990. And it looks something like this. It'll give you some nice graphs showing the traffic that's going through Linkerd. And, oh, sorry, we have to pause for just 1 minute while we make sure these questions are working properly. All right, sorry about that. Hopefully that link at the top of the slides is now visible and working, if it wasn't before. That is where you can submit questions for me to answer at the end. If it's not, if you can't see that, then please sign into our Slack and there'll be people answering questions in there. Again, if you need the link, that's slack.linkerd.io. The channel is Linkerd 101. And hopefully we'll get the questions working here, but if not, please go ahead and ask questions in there and there'll be some people answering questions. All right, so I was talking about the dashboard. This is served on port 9990, and this will show you, the success rate and the request rate of all the requests that are going through your Linkerd instance. It will show you the clients that Linkerd has dynamically generated based on the traffic that's going through it, and you can see that it's got the server there as well. So this gives you a nice view into what's going on. It's also worth noting that this is just the data from that one individual instance of Linkerd. If you want aggregated metrics across all of your Linkerds, that's not going to be shown here, but there are a few ways to do that. In particular, we've got a really great blog post about Linkerd and metrics that, again, I'll put a link to it at the end that shows you kind of how to use Prometheus and Grafana to aggregate metrics across all your Linkerds and display that in an aggregated dashboard. But this dashboard just is for an individual Linkerd. So hopefully that's a really quick overview about what Linkerd is and how it can be used. The next thing we're going to talk about are the deployment models and how you can deploy Linkerd into your stack and how it interacts with your application. So the first kind of deployment model that I want to talk about is the one that we usually recommend. It's called a service mesh. It's also called per host. And the idea here is that you will deploy one Linkerd on each of your hosts in your cluster. And any time you want to make a service call from one service to another, instead of making that call directly, your service will instead send that request to localhost on some known port where Linkerd is listening. And so you can see in the diagram that the service for the application sends the request to Linkerd. The Linkerd on that host forwards it to another Linkerd on the destination host, which then forwards it to the final application. And so in this sense, Linkerd kind of wraps the network call. And this is really powerful because you get metrics on the client side, you get metrics on the server side, and you also get Linkerd being able to upgrade the cross-host request. So for example, this can be used to add TLS to that cross-host request so that all your traffic on the wire is encrypted, or you can do other protocol upgrades like Thrift to ThriftMux, or HTTP1 to HTTP2, so it's really powerful. Again, we've got a really great blog post on this subject about why we do it this way, called daemon sets is what this is called in Kubernetes, because you're deploying one per host. But you can do this in other environments like in Mesos or other environments as well. An alternative to that deployment model is called the sidecar model. This is where instead of deploying one Linkerd onto each host, we deploy one Linkerd instance alongside each application instance. So in Kubernetes, this would be the equivalent of putting a Linkerd in each pod. And this is going to be a little bit more expensive because you're running more Linkerd processes, but it does have some advantages, especially if you want more specific and targeted TLS certs. For example, if you want a specific cert for each application, then you're going to need a Linkerd in each pod or running alongside each application instance. So it's more expensive, but there are some advantages. But in each of these cases, you have your application sending traffic to a local Linkerd, be that pod local or host local, and then Linkerd kind of takes care of the rest, and the request gets to its final destination through those routing rules. Okay, so next we're going to talk about what happens when you send Linkerd a request. So when you send a Linkerd request, you might do it, just for testing purposes with a curl. So that top line says, send this request to localhost on port 4140 where Linkerd is running, and set a host header. So we say host equals foo. Another way of kind of accomplishing the same thing is by using the HTTP proxy environment variable. And so we say use localhost 4140 as the HTTP proxy, and then we can just curl foo. And that has the same effect. It'll send it to the localhost Linkerd, and it will set the host header equal to foo. And so when we do that, what happens next? Well, there's 4 things that happen, 4 steps. The first is identification, and this is where we assign a name to that request, and we call it a logical name, and I'm going to talk more about what that means. The second step is called delegation. This is where those routing rules that we were talking about come into play, and it's going to transform that logical name, which is kind of like the name of the service that you want to talk to, into a concrete name, which is a specific cluster, so a specific instance in service discovery or something that we can, concretely route to. The third step is binding, where we take that concrete name and we resolve it into an actual list of addresses, so IPs and ports. And then the fourth step is load balancing, where we pick one of those IP port pairs and we actually send the request there. So the first step is identification. And so when Linkerd receives a request, the first thing it does is it assigns it a logical name. And a logical name is like the name of the service that you want to talk to. So this is something that's client addressable. So this would be something like if you want to talk to the auth service, this would be auth. If you want to talk to the transaction service, this would be transaction, or the payment service. This is kind of like a logical ID that you want to talk to. And this is something that the client would specify. And notably, this is agnostic of cluster details. So we're not talking about staging versus prod. We're not talking about DC1 or DC2. We're not talking about versions, because the client shouldn't have to know about these things. The client should just send a request and say, I want this request to go to the service that handles these requests. So I want this request to go to the user service, for example, or the foo service. And the rest should be taken care of. So logical names typically look something like this: HTTP 11 get foo, where that's a prefix that specifies this is HTTP. Then the protocol version 11, the HTTP verb is get, and the host header that we set is foo. We actually want to move away from this naming scheme a little bit in the future to something more simple, which is just a short prefix like S, and then the name of the service we want to talk to. So sfoo would be a simpler logical name, and we want to kind of move in that direction because this is a request bound for the foo service. The second step is delegation, and this is where we're going to turn that logical name, like sfoo, into a concrete name. And a concrete name is something that's actually a routable destination. So usually this specifies an entry in service discovery. So, a specific entry in console, or a specific app in Marathon, or a specific, service in Kubernetes. And so in this example, we've got, hash io.l5d.kubernetes, and this says use the prod namespace, the HTTP port, and the foo service. So this is something that's actually routable. This is a real cluster. And yeah, like I said, this is usually an entry in some kind of service discovery. A little bit of a note on the syntax here: all concrete names will always start with a hash or a $, and the reason for that is just to make them easily identifiable and to tell you that this is something that we're going to look up in a namer. So speaking of namers, the next step is binding. And binding is where we take that concrete name and we find the namer that matches its name. So in this case, we would say we need to use the Kubernetes namer. So if you remember on a previous slide where I was talking about configs, there's that block of namers at the top. And so this kind of tells us all the namers that we have to work with. And a namer is a integration into service discovery. So this says, tells you which namer to use, and says, use the Kubernetes namer, look up this name, and give me the IP and ports for all of the destinations that match that name. And so it turns this concrete name into an actual set of addresses. So some examples of namers that Linkerd kind of supports out of the box: Kubernetes, Zookeeper, Marathon, Console, Curator, and this is extensible. So it's easy to write plugins that talk to other forms of service discovery, and you can add your own. Another one that's really useful for testing is the FS namer, which just looks at a file in your file system for a list of addresses. So we use that a lot for testing and demo purposes. The final step is load balancing, And so this is where we take a look at that list of addresses, and we pick one of them in order to send the request to. And as I kind of alluded to earlier, we can do some intelligent things around load balancing. Because we know how long requests take based on the historical data we have, we can send more requests to nodes that are faster, less requests, fewer requests to nodes that are slower. And there's a number of different load balancing algorithms that we can use. One of the most interesting ones is called EWMA, which stands for Exponentially Weighted Moving Average. And it's really smart about picking the hosts that are performing well and not sending much traffic to the hosts that aren't performing well. And like I've been doing earlier, there's another shout out to one of our great blog posts here about load balancing and why EWMA performs so much better than round robin or other more naive load balancing schemes, or load balancing schemes that just work at the TCP layer and can't know about request and response level information. The gains you can make here are really fantastic. Of course, not everything always goes according to plan. Sometimes you send a request and it fails for some reason. Either there's a network problem or there's an error in your service and the request fails. And this is where retries can kick in. So if you send one request to one endpoint and it fails for some reason, you can retry that request, or Linkerd rather can retry that request, and it will go hopefully to another endpoint where it will be successful. And this takes advantage of a feature called failure classification, where we take a look at the request and the response that initiated it and determine, is it a failure, is it a success, and if it is a failure, is it safe to retry? And exactly the logic that goes into that is configurable. We provide some good defaults for HTTP out of the box where we look at response codes and say that 500s are probably an error, and depending on the HTTP verb, if it's a GET, it's probably safe to retry. But this is all configurable. So you can specify which requests are safe to retry, which requests and responses you should consider to be failures. And the other thing that we can do is that if a certain endpoint is returning a lot of failures, we can kind of know that that endpoint is not healthy. Something's wrong with it. And so that's where circuit breaking will kick in, and Linkerd will just stop sending requests there. Obviously, something is wrong with that host. It's in a bad state. We should just not send any more requests there until we can detect that it's healthy again. So this kind of summarizes what I just talked about. There's the 4 steps again: identification, where you get the request and give it a logical name, which reflects the service that the client wants to talk to. Again, the client doesn't know, am I talking to prod, am I talking to staging, am I talking to one DC versus another? It just knows that it wants to send a request to the foo service. And then delegation is the next step, where that name, that logical name, gets turned into a concrete name. We're going to talk about exactly how that happens a little bit later, but it gets turned into a concrete name that specifies a specific cluster. So that's where you would specify information like data center, environment, version. Then we use one of the configured namers to talk to service discovery and get back a list of IP addresses, physical addresses that we want to talk to. And then finally, there's load balancing, where we pick one of those addresses according to some load balancing algorithm and actually send the request along. So that's kind of from the time that the request comes into Linkerd to the time that Linkerd sends the request out. Those are kind of the main steps that happen along the way. So next we're going to talk about Dtabs and dynamic routing. So this will kind of clarify a little bit what I was talking about earlier. How does a logical name get turned into a concrete name? And what are those routing rules that we specified in the config? So those routing rules are called Dtabs. It's short for delegation table. And this is the process by which we turn a logical name into a concrete name. So this is step number 2, delegation. And Dtabs work by doing prefix replacements on the name. So on the top left there, we have a dtab, And you'll notice that they're all these kind of arrow transformations. So we've got a left-hand side, and then an arrow, and then a right-hand side. And the way this works is if you're given a name like sfoo, a logical name, we look through those rules and we look for ones where the left-hand side matches a prefix of the name. So in this case, we'll see that that third rule, /s, matches our name on the left-hand side. So we can perform a replacement. So we replace /s with /env http. And then we get the second row there. So we get env http foo. The foo is left unchanged. The s is replaced. And then we go back to the rules again. We look for another rule that matches. And here we see there's a rule that starts /env, which is the second rule there. And again, we perform that replacement. So env is replaced with serve prod. And then we go back to the rules and we perform another replacement. SRV is using that first rule replaced with hash io.l5d.kubernetes. And then we have the rest of the name, which is unchanged, prod http foo. So just by kind of repeatedly applying these replacements, we transform the logical name into a concrete name. And once we get to the hash, we kind of know we're done. That's a concrete name because it starts with that hash symbol. And you may be wondering, why is this so complicated? Why are there so many steps involved? We're going to talk about that pretty soon when we talk about dynamic routing. But for now, I'll just tell you that this is how it works. We do these replacements using the DTAB rules to transform from the logical name through a number of replacement steps, finally into the concrete name. Now, this can be a little bit hard to follow in your production environment. It's not always completely obvious what's going on. So one of the best ways to kind of debug this kind of thing or to understand it better is to use the DTAB playground. So in the Linkerd admin dashboard that I showed earlier, this is running by default on port 9990, there's a second tab called Dtab. And this is where you can kind of type in logical names into the top there. It'll show you what the current Dtab is, and it will show you all the rewrite steps that are applied to that name. So this will show you, how is your name transformed from logical into concrete, and if it's not being transformed correctly, you can kind of see at what step that fails. So this is really, really useful in figuring out what's going on with your Dtabs. Now, the reason that we kind of break these Dtab replacements into multiple rules and multiple steps is so that we can do these overrides. And so what I'm showing here is that if you add a fourth rule that says sfoo transforms into serve staging 1 http foo, that can change the delegation process. So it's important to note here that these rules are interpreted from the bottom up, so rules at the bottom have higher precedence. And what this override rule does is it says, if you're trying to talk to the foo service, if you've got a name that's sfoo, then instead of going to the prod namespace, substitute the staging 01 namespace. And so from the same logical name, we get a different concrete name. We get the concrete name where the namespace is staging 01, just by adding this override rule to the bottom of your Dtab. And so this is really, really useful, and I'll show you why. The reason why this is so useful is because you can do per request overrides. So if you send a request and you add a special header called L5D Dtab, and you specify a rule in there, that rule will be appended to the Dtab for that request. And it will get propagated from one service to another if your services are forwarding headers. And the result of this is that if you have this override rule, then anytime that request wants to talk to the foo service, instead of using the normal rules and talking to the prod namespace, it's going to substitute the staging 01 namespace instead. And so in this case, you send your A service, A talks to B, and then B talks to foo, but instead of talking to prod foo, you're going to talk to staging 01 foo instead. And so this is a really, really easy and powerful way to do ad hoc staging and talk to a specific staging instance in the context of your production stack. And if you kind of want more details about this, we've got a really great blog post that talks about it a little bit on dog fooding and how you can use these headers to talk to specific versions of a service for the purposes of dog fooding. So this is kind of really great if you just want to do a little bit of ad hoc testing. It's important to note here that all requests that don't have that header are still kind of going along the normal production track. They're going A to B to foo and prod because they don't have that override header. So this doesn't affect prod traffic. This doesn't affect any traffic that doesn't specify that header. So it's really safe. You're not testing in production. But sometimes you do want to change production traffic around. And so how do you do that? Well, you could go to all of your Linkerd configs and update the Dtab and add a rule that shifts the traffic somewhere else and restart all your Linkerds. But obviously, you don't want to do that. What you really want is a centralized place where your Dtab is stored and managed. And so that's what Nameerd is. So Nameerd is another project that works alongside Linkerd. It's a service that runs as a centralized Dtab store. And you, instead of configuring your Dtabs in your Linkerd configs, instead you configure your Dtabs in Nameerd. And all your Linkerds will talk to Nameerd and listen for updates, and Nameerd will take care of all of the naming. And so this means, one, that you only have one single source of truth for your Dtabs. You don't have to keep them in sync across all your Linkerds manually. The second thing it means is that you can push updates to your Dtab in Nameerd, and those updates will go out automatically to Linkerds without needing to restart them. So this allows you to dynamically change your Dtab rules, dynamically change your routing policy on the fly just by pushing updates to Nameerd. And so this is really powerful. This means that you can change the way your production requests go on the fly. It gives you kind of a centralized place to do routing policy. And the third thing that it does is that it sits in front of service discovery, and Linkerd just needs to talk to Nameerd, Nameerd talks to service discovery. And so this means if you've got thousands of Linkerd instances, you're not creating thousands of requests to your service discovery and completely overloading it. Nameerd takes care of that. And it will also cache that information from service discovery. So if you have all of your Linkerds kind of watching for updates to a single service, you're not going to completely overload your service discovery. Nameerd is going to cache that. It's also important to note that service discovery is often a single point of failure in systems that rely on it, because if you don't know where your services are, if you don't know where your instances are, you can't talk to them and nothing works. So with Nameerd in the picture, that information is cached, and if your service discovery goes down, your instances will still know where things are, or where things were at the point that service discovery went down. And as long as nothing moves, you'll still be able to take traffic. Everything will still work, for a while. It's also worth noting that if Nameerd itself goes down, Linkerd caches that information as well. So Linkerd will continue to route using the last known good information. And as long as nothing moves around, things will keep working properly, hopefully giving you enough time to figure out the service discovery issue and bring it back online. So this is useful for a lot of different things. You can use this to do cross-DC failover. So if you want to send all your traffic from one data center to another, you can just push a Dtab rule to Nameerd, and it will kind of have that override effect, and all the traffic will shift. It's really cool. You can do things like blue-green deploys, where you deploy two different versions of the same service, and then you push Dtab rules to Nameerd to slowly shift traffic from one version to the other. Make sure that it's working okay. If it's not, you can easily revert those changes and go back to the old version. And we've got getting almost tired of saying this, but we've got a really great blog post on that topic as well, using Linkerd and Nameerd to do continuous integration, continuous deployment by pushing these rules out. You can use Nameerd to do legacy migrations. So if you've got an old system and a new system, you can kind of do the same thing where you push these DTAB rules to slowly shift traffic off of the old system and onto the new one. And if something goes wrong, you can easily revert that update and go back to sending traffic to the old system. So it's really a safe way of shifting traffic around. And then you can also use this as a kill switch. If you've got a service that's behaving badly, maybe it has a security vulnerability or some other problem, you can just kill traffic to it at the traffic layer by sending a DTAB upgrade or a DTAB update that says, don't talk to this host anymore, or don't talk to this service anymore. And this is useful if you want to, for example, kill traffic to a service without killing the service itself. If you want to, make sure that its logs are preserved or that you can reproduce some bad behavior, you can take traffic away without actually killing the service. So that's most of what I wanted to talk about today. I know we had some issues with the questions. Hopefully you were able to submit some questions. I see some here, so we're going to have some time now for me to answer those. Before I do, I just want to put up this slide here that's got some great links. So the Linkerd website has lots and lots of information, really great docs, really great guides. I highly recommend you check it out. I plugged our blog posts repeatedly. They're really, really great. If you go to blog.buoyant.io, I really encourage you to read through the stuff there. There's some really great examples of how Linkerd and Nameerd can be used to do some really cool stuff, especially if you're on Kubernetes, but if you're on other environments too, it's just awesome stuff. Our Slack is really active. If you have any questions that we're not able to get to today, or you just want to talk about Linkerd, there's always people in Slack. It's a really active place and really nice place to hang out and talk about this stuff. And then we also have an email group as well. So that's another question or another place you can ask questions. If you don't think it's appropriate for Slack, you can fire an email to the group and someone will respond. All right, so I will now start with answering the questions. So we've got a question here. It says, when does the lookup in the service discovery namer happen? Dynamically, when a request comes in, is it cached, and how does it update? Yeah, so the way this works is that the first time a request comes in with a particular concrete name, we'll do the lookup of that concrete name in service discovery, and then we'll keep a watch on it. So as service discovery updates, Linkerd will update its information about that name as well. So we'll just keep watching that for updates, and as they come in, we'll update what we know, and as requests flow through Linkerd, they'll use the information it has. So the first request for a particular concrete name kind of kicks that off, and then after that, it's just kept up to date. Next question is, would be interested in the question of delegation in Thrift as opposed to HTTP, where there's no verb. What does something like sfoo look like when it comes to Thrift delegation? Yeah, that's a great question. In Thrift, there's not a lot of information to work with. HTTP is pretty rich in that we get a host header, which we can use as a destination ID. Thrift doesn't have anything like that. So with just plain Thrift, what you usually have to do is just simply do kind of a static mapping of port to logical ID. So you might say everything that comes in on this port is given this logical ID, everything that comes in on this port is given this logical ID. There are some enhancements to the Thrift protocol that Twitter did that include a little bit more information in the envelope, and you can specify a destination ID there, but that's pretty non-standard. I don't know how many people are doing that. So yeah, with Thrift it's a lot more difficult. There's less information to work with. Next question is, how would you get traffic from a few F5s to Linkerd where multiple domain is translated into IP port, but the request domain is in the header? Would you use some sort of software like HA proxy, or does Linkerd deal with this kind of routing? Where multiple domains is translated into IP port. I'm not sure I fully understand the question, but Linkerd can, the way that Linkerd assigns logical names to a request is something that's configurable and something that you can write a plugin to do. So by default, we'll look at the HTTP. For HTTP, we'll look at the host header, but you could look at other things as well. You could look at the domain. You could look at other aspects of the request. But at the end of the day, the idea is that from that request, you should derive somehow a logical name, like a service name for that request. And then from there, it can go through the other steps: delegation and binding, and load balancing. I'm not sure if that answered the question, but if you have follow-on questions, please pop into the Slack and we can have a longer discussion. The text on the slides is quite small. Will they be available later? Yes, I'll be happy to post the slides later on. So I'll post the slides and I'll post a link in the Slack and potentially on the group as well, the invite group. Okay, we've got some more questions that came in on a different instance of the link, so I'll answer those as well. One question is, how do we best debug Linkerd? Yeah, I mean, it depends on what the issue is. One of the best ways for debugging Linkerd is, as I said, to look at the DTAB playground and see how your names are being resolved and make sure that your DTAB rules are being applied in the way that you think they are. Another thing to do is the Linkerd logs are pretty rich, so if something's going wrong, usually there'll be something in the logs that can kind of point you in the right direction. And kind of as a last resort, you can always look at things like a TCP dump to see the traffic coming in and out of Linkerd and what's going on there. But usually it shouldn't have to come to that. Another question is, what is the smallest useful architecture for using Linkerd? I mean, anytime that you are using service discovery, already Linkerd is useful because you don't have to build service discovery logic into your application. You can just, go through this proxy that takes care of it for you. Other than that, it will solve kind of whatever problem that you have for it. So if you want to do things like dynamic routing, then obviously it's useful. If you want to improve your success rate without having to think about retries in your application, it's useful there. If you want to improve your latency, especially your tail latency, then the load balancing aspects are really useful there. So it's kind of useful for, it depends on what problems you have, but even in really small architectures, those problems can exist and Linkerd can solve them. The next question is, say I'm using Kubernetes and Nameerd is not available. Can I propagate configuration changes to Linkerd by updating the Kubernetes config map and reloading Linkerd somehow? You can propagate updates to the config map and restart Linkerd, and it will pick those up. But Linkerd doesn't have any kind of hot reloading, so Linkerd would need to restart to pick up those changes. So if you want to make dynamic changes to Linkerd, then Nameerd is definitely the recommended approach. Next question is, what should the Linkerd configs look like? If we have routing between Linkerds, we have service A on host 1, service B on host 2, and Linkerd on each. Service A sends request for service B. Its Linkerd forwards the Linkerd on host 2, which forwards to service B. How does local routing work? Okay, yeah, let me pull up one of your earlier slides. That's a good question. Right, so I think this is what the question is about. So here we've got an application talking to Linkerd. Linkerd forwards the request to another Linkerd, and finally that Linkerd forwards it to the final destination. So usually the way this is set up is that we'll configure two different routers in the Linkerd. One router is called outgoing, and one router is called incoming. And the outgoing router is where you will send the request initially. So you'll have your service, sends a request to Linkerd, that's the first hop there. It goes to the outgoing router. and that will use Dtabs, use one set of Dtabs to forward that request to the other Linkerd that's running on the same host as the destination. But it will send it to the incoming router of that Linkerd. And the incoming router will have a different set of Dtabs, a different set of rules, which will then forward that request to the application itself running on that host. So there's a different set of rules for outgoing versus incoming, and that's how this we call this linker to linker, how this linker to linker setup works. Next question is, any suggestions for debugging Dtabs if we don't have access to the UI due to prod, security, firewall restrictions? Dtabs they seem complicated, but you can always kind of go through those substitutions by hand. It's a really there's only one thing to know about Dtabs, is that you do these replacements on the prefixes. So you can easily do that by hand and see how they work out. You can also just run a Linkerd on your laptop or on your computer and go to the Dtab playground there and just play around with it and make sure that it's working how you expect it. You don't necessarily have to go to a prod instance in order to just play around. I think that's all the questions there were. If you have any other questions or you think of something later, please either stop by our Slack or send us an email or get in touch. We are kind of always happy to answer questions and to hear about people using Linkerd. So I hope this was interesting and informative, and thanks you all for coming.